Okay, next I want to talk about a type of vulnerability that's actually quite common, but few developers know about it. A race condition is a type of bug where timing is crucial and where misused timing or bad timing can lead to bugs or sometimes vulnerabilities. In order to introduce race conditions, I want to give you a brief reminder about how processes work on computers. Usually what computers do is something called preemptive scheduling. That means on one core on a system only one program is running at a time. So imagine you have a single core system, just to make it easier for now. What would happen is you have different programs running, for example Thunderbird for emails, Firefox to browse the web, and GIMP to do photo editing. And what happens is actually all of these programs get a time slice, and then the operating system, the scheduler, just stops them, lets another program run, stops it, lets another program run, stops it, lets another program run, and it switches between running those programs so fast that you can't tell as a user that they're actually being stopped and started again. So this is preemptive scheduling. The processes themselves don't notice that they have been interrupted because it happens transparent for them by the operating system. So now what is a race condition? Well, if you think about, there's a global information store, let's say it's a global variable in the memory, for example, and you have two programs or two threads running and accessing the same global information. So the first process does a load. It loads the counter from memory into a register, then it increments the counter, then it saves the counter. A second process or thread also loads the counter, increments the counter, and saves the counter. So the counter has been loaded and incremented 2 times. Therefore the value should be 2, right? Well, not if a race condition happens. Now imagine the first process loads the counter and increments it, and then the operating system just stops the process and takes the next process. So now it's the next process's turn. It loads the counter, it increments the counter, and it saves the counter. Now this process is done. The operating system gives control back to the first process. Now, the first process had loaded the counter from memory into the register before that. So in this process's register, the counter's value is still 0. So it incremented it afterwards. So before the scheduling happened, the counter value in this process was actually 1. So now it saves the counter from its register to memory, and now the global counter is 1. Even though it has been incremented twice, the global state is 1 because of a race condition.